Statement we have the state of stress at a point is shown on the element. Determine A, the principal stress, and B, the maximum in-plane shear stress and average normal stress at the point. Specify the orientation of the element in each case. So we see here we have this element with the appropriate, in this case we have a compressive stress. So we're going to have sigma x being negative 30 ksi. Sigma y is obviously 0. And the shear stress along the xy plane is negative 12 ksi because this shear stress is going downwards along the y direction. In other words, negative here instead of upwards. So now let's go ahead and solve for the principal stresses and of course also solve for the angle in which the principal stresses occur. So after plugging it into the principal stress equation, we get negative 15 plus or minus 19.2 KSI. Since we know sigma 1 is greater to sigma 2, we have sigma 1 being equal to 4.2 KSI and sigma 2 being equal to negative 34.2 KSI. Now the question is which one is going to be the normal stress along the new x prime direction and which one will be the normal stress along the y prime direction. And this is where we're going to use the equation for the theta p. So the theta p is equal to the tangent inverse of tau xy divided by sigma x take with sigma y divided by 2. All this divided by 2 to finally solve for that angle. And so plugging in the values here give us. So we get 19.3 degrees. Now this is where we could go ahead and use the plane stress transformation equations, plug in this theta value and solve accordingly. Let's go ahead and do that. So this is the plane stress transformation equations, right? We have one for sigma x prime, we have another one for sigma y prime. And so what you do is once you solve the angle for the maximum principal stresses, you go ahead and plug it in this equation with all the other variables and see which value is for the x prime direction. Is it the negative 34.2 ksi or is it the 4.2 ksi? And that will identify which is your sigma 1, along what direction is your first principal stress, and along what direction is your second principal stress. So let's go ahead and solve for this equation. Let me plug in all these values and let's see what we get. And we get the sigma x prime is equal to negative 34.2 ksi, which is the second principal stress. So now we could go ahead and draw this element for the principal stresses. And here we have the element rotated 19.3 degrees, and we have the principal stresses drawn along the appropriate axis. And keep in mind when it comes to solving for principal stresses, in that case, there is absolutely no maximum shear stress or any shear stress developed for that matter. Now let's go solve for at what angle will the maximum shear stress be developed as well as the value for the maximum shear stress. So plugging in the variables for the maximum shear stress equation, this is what we get, the maximum shear stress being 19.2 ksi, and we have the average normal stress being negative 15 ksi. Now for the angle where this shear stress is developed, we have this whole equation here. Once plugging in for all the values, we end up getting negative 25.7 degrees. Now the same thing as we previously have done, we could go ahead and calculate using this angle, plugging it into the plane stress transformations for solving for the shear stress, and we could see whether this maximum shear stress is going to be positive or negative because it could be either or case. So as a reminder, this is a plane stress transformation for the shear stress along the x prime y prime. You plug in this value for the angle here that we solved for and solve for the shear stress. And we find that this shear stress or the maximum shear stress will be negative, right? This negative once you plug in and solve accordingly. So let's go ahead and draw out this element. And so here is the element ultimately having the average stress as compression along all the planes here. We have that angle theta s is equal to negative 25.7 degrees. and we have the maximum shear stress being negative 19.2 KSI. Similarly, as the principal stresses, right, sigma 1 is greater than sigma 2. This one, since it will be the smallest value, right, since we're dealing with the negative, but there's also the positive shear stress, this will be theta S2. And the other relationship was theta S1 is equal to theta S2 plus 90 degrees. We see theta S1 being equal to 64.3 degrees. Now, the only reason I bring this up is because the previous relationship that I shown was theta S1 is equal to theta P1 plus 45 degrees, since that's the offset between the angles 45-degree angle, and you'll see that this will in fact meet the condition, right? Theta S1 is equivalent to 64.3 degrees because the theta P1 is 19.3, which is the same equivalent. And so this is how you solve for the principal stresses as well as the maximum shear stress developed at a particular angle for both of the cases. And it's very important for the design to make sure we're accounting for the maximum shear stress developed as well as the maximum normal stresses or the principal stresses for design such that the object won't fail. And knowing the angles along where these maximum normal stresses as well as the shear stresses develop, sometimes objects may fail along that same direction based off the angle where the maximum shear stress is developed or where the principal stresses are developed. So that's one fun fact there. It's pretty interesting.